Hi everyone, thank you for tuning into my talk. My name is Pete and I'm a PhD, soon to be postdoc here at UCL. And today I'll be talking to you about using movies to probe the neurobiology of anxiety. So quick disclosure, I was previously employed by Roche, but I currently hold no formal relationship with them. So I'll just start with this quote from the godfather of suspense, Alfred Hitchcock. Now, there is no terror in the bang, only in the anticipation of it. And the reason why I think this is useful is because it can help us conceptualize anxiety. So anxiety is a healthy, normal, adaptive emotional state that we all experience from time to time. Unlike fear, which we typically think of as an acute response to certain imminent threats in the environment, it's like the bang. Anxiety is more the anticipation of the bang. So it's elicited by uncertain threats in the environment, and this may be in space and or in time. And this is considered adaptive because it can help tune attentional and perceptual systems to help us detect and identify potential threats in the environment. But it also engages peripheral physiology. So we see increased engagement of the autonomic nervous system, so increased sympathetic activation and decreased parasympathetic activation. And this does things like increased heart rate, so it provides oxygen-rich blood to our muscles to help us kind of engage in physical exertion, which can help us with fight or flight like behaviors, which avoid harm. But as well as kind of within individuals, anxiety being evoked as an emotional state, it can vary between individuals. So different people have different levels of trait anxiety, which means an individual's disposition towards states of anxiety. Now, this can vary just kind of subtly at subclinical levels, but when it reaches severe levels, we typically think of this as a pathological anxiety because people are engaging in states of anxiety so frequently and so intensely, it's actually impairing their day-to-day function. So traditionally, we've studied anxiety by using threat of shock paradigms, wherein you hook people up to a shock machine and you tell them, okay, in the next minute, you may or may not receive shocks. We record kind of behavioral measures and biological measures, and then we can contrast these to blocks where we don't threaten to shock people. And what we've learned from this is that there's this kind of broad cortico-subcortical autonomic network which appears to drive anxiety-relevant behaviors. So this includes, but is not limited to, DMPFC, insula, SGACC, VMPFC, bed nucleus striaterminalis, hypothalamus, amygdala, and paraqueductal gray, all of which communicate with peripheral physiology, i.e. the autonomic nervous system. And together this can help tune perceptual systems like attentional biases towards threat, and activation within this network can amalgamate in the subjective experience of anxiety. But we've got to ask ourselves, is this how we experience anxiety in our everyday lives? It's not often that we're kind of hooked up to these machines and told you may or may not receive a shock in the next minute. And so a question that I was getting at for my PhD is, do our findings from the anxiety literature generalize to these more naturalistic settings? And so for this, I've been using movie fMRI. And what we've shown is that individual differences in trait anxiety can shape responses within this network, but moreover, that the association between trait anxiety and responses in this network vary as a function of suspense. And so for some connections, these are primarily apparent during low suspense scenes, and for other connections, they're primarily apparent during high suspense scenes. And we see this both for measures of self-reported anxiety, but also for measures of attentional bias to threat or threat vigilance. And we see kind of individual differences relating to connectivity across this whole network or across large parts of this network. But importantly is that in a follow-up study, I looked at the exact same individuals using the exact same anxiety measures by looking at connectivity while at rest. And we actually find that these effects weren't emerging in the same subjects, but during resting state scanning, which suggests that there is utility in kind of providing these anxiogenic perturbations to the system, which can elicit anxiety-relevant idiosyncrasies. But all these results I just presented, they're just correlations between self-reported anxiety and brain activation. They weren't actually telling us really kind of what sort of processes this activation is associated with. And so a kind of follow-up question that I was looking at is whether perhaps activation and connectivity within this network might be reflecting alterations in brain-body communication, specifically with the autonomic nervous system. And so to get at this question, I used the Caltech Conte Center dataset. Here we had 29 subjects following exclusion from 55. Subjects underwent fMRI scanning. Either they had two conditions. All subjects either watched an anxiogenic suspenseful clip for 8 minutes or a non-suspenseful control clip for 5 minutes. And so the suspenseful clip, Bang You're Dead, in brief, is just about a child who finds a gun. He believes it's a toy gun, but the audience knows it's actually a real gun, and he kind of goes around waving it, potentially like pretending to shoot people. And we've validated behavioral ratings that this does actually elicit anxiety quite effectively. But importantly, there were also pulse oximeter recordings. So what we did with this data set is we extracted time series, neural time series across this defensive response network, both in regard to activation as well as dynamic connectivity. And then using the pulse oximeter recordings, we also generated time series of heart rate using our pipeline we developed a couple of years ago called Rapid HRV. Now, essentially, we wanted to generate a proxy for neural autonomic communication. And so here we use the term coherence so as to be quite theoretically neutral. But essentially, what we wanted was just a measure of how similar these two signals were in each condition. So we took 3 approaches to this. We took a very data-driven approach, dynamic time warping, which essentially just non-linearly warps the two signals in time so as to optimally match them, the end product being a distance metric. Our second coherence measure was derived just through bivariate correlation. So we took HRF lagged heart rate time series and just correlated them with the bold signal. And then for an exploratory analysis, we also looked at cross-correlation maxima. So what this did is essentially kind of introduced varying lags to the heart rate signal. And then this was correlated with the bold at each of these lags. And then it determines which lag has the optimum kind of maximum correlation. And then it just selects this maximum correlation. And this is data driven, but it is kind of each condition is treated equally. So the maximum correlation is selected but for both conditions separately. And essentially what we end up with is a measure of kind of brain-body coherence during the anxiety condition and brain-body coherence during the control condition. And all we did is submit these to pair sample t-tests. And our expectation was that activity within this network increases activation within the sympathetic branch of the autonomic nervous system, which would then increases heart rate. So we should see a kind of increases in the association between defensive response activation and heart rate and the coherence between these signals as a function of the anxiety condition. Now onto our actual results. For our dynamic time warping measure, we failed to find any effects. And I think this is largely due to the kind of unnormalized nature of the distance measures generated by dynamic time warping. For our second measure, bivariate correlation, so again, this was just correlating heart rate with bold. We failed to find any associations at the level of activation, so this is the diagonal. But we did find some associations with dynamic connectivity. So specifically, the coherence between amygdala prefrontal responding and heart rate was modified as a function of condition. So this was amygdala DMPFC and amygdala SGACC. Actually, what this looked like was kind of in the inverse direction to what we predicted. So in the non-suspenseful control condition, there was a positive association between amygdala prefrontal dynamic connectivity and heart rate. But in the suspenseful anxiogenic condition, this association was either negative or non-significant. So we saw these overall reductions in brain-heart coherence as a function of the anxiogenic condition. Now I'll get onto the interpretation in a sec, but I'll just quickly show the exploratory cross-correlation maxima results. Here, essentially, we again found reduced coherence between activation in VMPFC, precuneus, and bilateral putamen. But the interesting thing here, I thought, was that actually when we look at the delays from these cross-correlation maxima, is actually suggesting that there's the kind of optimal delay is 16 seconds of heart rate preceding bold activation. And this is after accounting for hemodynamic lag. Now, this needs to be explored further, but I just thought it was worthwhile mentioning. Okay, so on to the actual interpretation. Obviously, we interpreted that, or predicted that as activation in this network would increase, so would heart rate as a function of anxiety. Well, however, that's not what we found. Instead, what may actually be happening is rather than relating to activation within the sympathetic branch of the autonomic nervous system, these effects could relate to parasympathetic withdrawal. So as activation in this, or connectivity between amygdala, DMPFC, and SGACC increases, it's actually telling the parasympathetic branch to not slow the heart down, because the parasympathetic branch is typically associated with kind of rest and digest behaviors. And as such, this could actually be kind of related to parasympathetic withdrawal, which typically actually occurs at a much faster time frame than sympathetic activation. The other possibility is that these results could reflect interoceptive integration, so that during the anxiogenic condition, participants are actually basically paying less attention to their internal bodily signals. And this, when you think about it, it could make sense because, if a key function of anxiety is to kind of seek out, detect, and identify potential threats in the environment, when you're engaged in such a rich, complex stimulus, you may be essentially just attending very heavily to the stimulus itself, in this instance, kind of suspenseful movie, and paying less attention to your own internal bodily signals. So as for future work, I think it'll be important that, of course, we have longer scans. These were 5 to 8 minute scans, so it'll be very important to conduct this across longer time scales. See whether effects generalize across different movies. It's all well and good just moving from tasks to movies, but I think it's just as important that we show generalizability across different movies. This was obviously a sample of just 29 people. It will be absolutely necessary to clarify whether these effects still emerge when we use bigger samples. I think it'll be useful for future work if we start to characterize these temporal lags between activation in the autonomic nervous system and brain activation, as well as using other physiological measures such as skin conductance or respiration. But most importantly, if a key goal of all of this work is to potentially kind of aid in the development of assessments and treatments for anxiety, it's very important that we actually study this in people with pathological anxiety. Here, this is just conceptualized around adaptive state anxiety, but I think it will be really useful to look at this at the level of individual variation, specifically in clinical samples, which is what I will be doing going forward. So hopefully I've shown you today that suspenseful movie watching is a useful platform for evoking anxiety-relevant neurobiological responses, and specifically that anxiogenic movies can elicit altered communication between the brain and the autonomic nervous system. So I'll just end by saying thank you to my primary supervisor, Ollie Robinson, my collaborators, Avram and Jeremy, the labs at UCL and Yale, my doctoral training program. If anyone wants to get in touch, please feel free to reach me on email or social media, and thank you for listening.